Okay, that brings us to buffers, because all buffers are this idea of common ion effect. So a buffer is simply a solution that resists a change in pH when limited amounts of an acid or base are added to it. And I use the term limited loosely because you'll be amazed how much acid and base we can add to a buffer solution and have the pH change by almost nothing at all. Okay, now that's really important, otherwise we wouldn't be here today. I'll explain why here in a second. But buffers contain either the weak acid and its conjugate base, or vice versa, its weak base and its conjugate acid. It depends on what pH you want your buffer at. If you want your buffer at a pH less than 7, so acidic, you're going to use the weak acid and its conjugate base. If you want a buffer that's basic, so a pH greater than 7, then you're going to use a weak base in its conjugate acid. So thus, a buffer contains both an acid and a base species in equilibrium, just like we saw with the common ion effect of the formic acid with the sodium formate. So here's just an example. So again, our bodies have are very susceptible to pH changes. Our blood, for example, has a pH of 7.4, and if it varies by more than 0.05, you die. So there's actually all kinds of different buffer systems within the body. The bicarbonate buffer system is a main one, but there's also phosphate buffer systems, since our DNA has this tons of phosphates in it. The body has tons of phosphate. So phosphate's also used as a buffer system within the body. And like I said, there's actually hundreds of other buffer systems within the body as well. But these are some of the main ones. So basically what happens is you start walking around or working out, whatever, okay, you're making your muscles do work. And what happens is that your muscles start to build up acid, specifically lactic acid, okay? And then there's also CO2 that's being produced as well. And so what happens is from the red blood cells, oxygen is transferred to the muscle cell, okay? And then the acidic proton is transferred to the hemoglobin. And so basically then what we form is we go from the hydrogen ion, and then there's the hydrogen carbonate ion. It forms carbonic acid, right? But we know that carbonic acid is unstable and dissociates into water and carbon dioxide gas. Well, in this case, it's not gas. It's actually dissolved in your blood. If it was actually a gas in your blood, that could kill you. That would probably cause a stroke. But we can absorb limited amounts of carbon dioxide into our body, right? That's why sodas contain carbon dioxide, okay? And then we could expel some of that carbon dioxide. So depending on what the acid level is in the blood, it's going to use this carbonate system going back and forth to keep that hydrogen ion concentration from changing. So this is what a buffer system does. So your body is going to determine exactly how much CO2 you should expel or not expel to maintain the acidity of your blood. Okay, so again, this is a simple biological buffer. So let's talk about buffer solutions. So let's consider a buffer with equal molar amounts of the acid, HA, and its conjugate base, right? The conjugate base, we simply lose H+, which means it would be A-. Okay, so that's our generic acid, HA, and its generic conjugate base, A-. So here it is, right? So we have, actually I want to change this animation. So here's our buffer, right? So here's our buffer. We have a significant amount of both the acid and the conjugate base, and they're in equilibrium with one another. But if I add acid to my buffer, it's going to cause that acid to react with the base, okay? And again, try to prevent that hydronium ion concentration from changing by, again, converting that added acid back to an undissociated acid, right? It's only the dissociated H3O plus or H plus that affects the pH. The undissociated acid doesn't affect the pH. So any added acid is going to react with the conjugate base to get rid of some of it and to go to the neutral acid. On the other hand, if we add a base to our buffer system, right, it's going to react with the acid to get rid of that extra OH and form our conjugate base. So that's all buffer is a common ion effect between an acid and its conjugate base. So you can see how it's preventing either the hydronium ion concentration or the hydroxide ion concentration from changing. And of course, we know that the hydronium and hydroxide ion concentration are related to one another through the self-ionization of water. Okay. Okay, so two important characteristics of a buffer. First is the buffer capacity. And the buffer capacity represents how much of an acid or a base that you could add to a buffer solution and without substantially changing the pH. So if you have a high buffer capacity, you can add a lot of acid or a lot of base to that buffer, and the pH is going to remain relatively the same. If you have a low buffer capacity and you add the same amount of acid or base, the pH is going to change a lot. So the higher the buffer capacity, the better. Now, we're going to very simply call the buffer capacity as the sum of the concentration of the conjugate base and the acid, the concentration of the conjugate base plus the concentration of the acid, okay? And we're going to give it a variable of beta. So that is our buffer capacity. Now, I really should change this with an approximately this. Again, if you take analytical chemistry, we'll see that it's a bit more complicated. It's actually a differential equation to actually account for the buffer capacity, but it is roughly, very roughly equal to this. And so that's the way we're going to look at it, okay? And again, in practicality, it works, okay? So it really does work this way. So again, our buffer capacity is just the sum of the concentration of the acid in the conjugate base. So that's the buffer capacity. So the greater that number, the greater the buffer capacity. The more acid or base you can add without substantially changing the pH. Now, the other factor is the actual pH of the buffer itself. And how do we figure out how to create an acid conjugate base system that would give us that pH? And we're going to find out that it's actually related to the Ka of the acid, okay, in the acid conjugate base. Or if we wanted a basic buffer, it's going to be related to the Kb of the base in its conjugate acid. But we're never going to treat it that way. We're always only going to look at the acid itself. So even if it's a base in its conjugate acid, we're only going to look at the conjugate acid. Okay? If it's an acid in its conjugate base, we're only going to look at the acid. So we're going to simply always relate it to Ka. Okay, so how do we prepare a buffer of a particular pH? Well, again, the buffer must be prepared from a conjugate acid-base pair in which the Ka of the acid is approximately equal to the desired pH. Okay. So let's consider a buffer of a weak acid, HA, and again, its conjugate base, A minus. Again, we see the equilibrium, and it simply looks like this, okay? So again, there's our acid in equilibrium with a conjugate base. The Ka for this expression is simply, again, our products each raised to the coefficient in a balanced chemical equation divided by our reactants. Again, we're going to ignore pure liquids, solids, or gases, raised to the coefficient in a balanced chemical equation. I'm going to rearrange this equation. That's all I did here is I multiplied both sides by HA. So I took the HA with a Ka. And then I divided both sides by the conjugate base. So I divided that. So that's why it ends up down here. So all I did was rearrange this equation for H3O plus, and that gave us this. Next step, I'm going to take the negative log of both sides. Okay, I'm going to take the negative log of both sides. Now, the negative log of let's say this is A and this is B, okay? Or let's say this is X and this is Y. Well, the log of X times Y is the same as the log of X plus the log of Y. But in this case, I took the negative log, so that's why it was negative and not plus, plus, okay? Then, through properties of logs, I'm going to flip these two. And when I flip these, all I do is change the sign in front of the log. Also, what is the negative log of the hydronium ion? What do we call that?
pH.
That's the pH. Now remember, the mathematical I don't know what you want to call it, symbol for negative log is P, right? pH. Well, we're going to call this the pKa. So again, we're going to invert this, which changes the sign, and then that's the pH, and we're going to call this the pKa. So the pKa is nothing more than the negative log of the Ka of that given acid. Okay? Well, this actually ends up being a very important equation. We call it the Henderson-Hasselbalch equation, and we could generically write it as the pH is equal to the pKa plus the log of our base, the concentration of our base, divided by the concentration of our conjugate acid. So this is the Henderson-Hasselbalch equation. This equation is only to be used for buffers. The reason why is you can't check your assumptions. So in the Henderson-Hasselbalch equation, they're automatically ignoring the plus and minus X terms without ever checking any kind of an assumption. Now that's fine for a buffer because all a buffer is trying to do is keep the hydrogen ion concentration from changing. But in other problems that we're looking at, that's not good enough. We're actually looking for a more quantitative change in concentration of reactants and products. So again, I repeat, the Henderson-Hasselbalch equation is only to be used when dealing with buffers. If you're dealing with a common ion and it has nothing to do with the buffer, you can't use this because you've got to check your assumptions of ignoring the plus and minus X terms. Okay? Okay, so there's our Henderson-Hasselbalch equation. Again, this relates obviously the pH of a buffer to the pKa value and this ratio of concentrations. So to prepare a buffer of a given pH, a conjugate acid-base pair with a pKa close to the desired pH is going to be required. Okay, so let's do an example then. So how would we prepare a 1 liter buffer solution with a pH of 4.0 in which the total concentration of acid and conjugate base is 0.01? Okay, so I understand what 1 liter of the buffer solution is. I understand that we want it to be a pH of 4.0, but what is this down here? What is this? This whole last line, what does that represent? Jada, what does this represent? Jada. Katrin, what do you think?
This might be wrong, but would that be the buffer capacity?
No, that's absolutely correct. That is the buffer capacity, right? And that's important to recognize because we're going to need this. So the buffer capacity is simply the sum of the concentration of the acid and its conjugate base. So this is the buffer capacity. This is beta is equal to the concentration of the acid plus the concentration of the base. Okay? Okay, so first we need to choose an acid with a pKa that's close to the desired pH. So for correct buffering, there should be significant amounts of both the acid and its conjugate base. So therefore, if we want to keep it, let's say, within a factor of 10, so that means that ratio has to be between 10 and 0.1. Well, when you take the log of that, that is a difference of 1. Okay, so this would be a difference of a plus or minus of a pH of 1. So that's what we're going to look for then. We're going to look for a pKa that is within plus or minus of 1 of our desired pH of the buffer. Again, let me repeat that. We're going to look for an acid with a pKa that's within plus or minus 1 of the desired pH of the buffer. So we want a buffer with a pH of 4. So I'm going to look in my tables of chemical data. Here's an abbreviated one. And the Kas are given, and I believe I give you the pKas in the tables of chemical data. Let me confirm that real quick. I do. I give you the pKas in the tables of chemical data, so you don't even have to go through and figure them out. Okay? And so basically, what acids could we use? And I want all of them. What would be all the acids that we could use? Hannah, what do you think? What are all the acids that we could use?
Of the ones shown, lactic and acetic.
Yeah, right. We could use either lactic or acetic. They are both within plus or minus 1 pH, right? Minus 1 would be 3, plus 1 would be 5. So anything in the range of 3 to 5. That's out of the range between 3 to 5. These are both over 5, but these are both within that range of 3 to 5. Okay? Now, which one would you actually choose?
You choose lactic because it has the least difference.
Yeah, exactly, right? So the smallest, we want the one closest to 4.0. Now, there might be a reason why you can't use lactic acid. Maybe lactic acid or its conjugate base, the lactate ion, actually reacts with something within the reaction that you're trying to buffer. And for that reason, you might not want to use lactic acid. Now, that's something that you'll have to, that's something you would do in the actual lab, and whatever profession you have, you would have to make those considerations. In this class, we're going to assume that none of our acid conjugate base pairs are actually reacting with anything in our solution. So we're simply going to choose the best. So in this case, again, this is closest to 4.0. So that means that our the acid conjugate base pair we're going to use is the lactic acid, and whatever the salt of its base is, right? Because the conjugate base is the lactate ion, but you can't buy a jar of lactate ions. You can only buy a jar of neutral molecules, okay? So maybe we'll use sodium lactate rather than, you know, or lithium lactate or potassium lactate. Now, why did I choose potassium, lithium, and sodium?
Those are soluble.
Okay, they are soluble, but there's also another factor.
They're strong.
They're the conjugate, right? They're the conjugate acids of the strong bases, which means they're not going to affect the pH. So that's why I chose the sodium, lithium, and potassium. Not only are they soluble, but in addition, they don't affect the pH of the solution. Only the lactate anion would as a conjugate base, a weak base. Okay.
Wait, I'm a little confused. If it's going to dissociate, wouldn't it break down and then contribute, or not, or would it cancel out?
What do you mean contribute? What?
Like, it's going to affect the pH or not?
Okay, so we're talking about sodium lactate, right?
Okay.
Sodium lactate. The sodium and lactate will dissociate into the sodium ion and the lactate ion. But the sodium ion will not affect the pH. The lactate will, right? It is the weak conjugate base of lactic acid. Again, it's just a common ion between lactic acid and the lactate ion.
Okay.
Yes, they will affect. The lactate will affect. The sodium ion will not affect the pH.
Okay.
Okay, does that make sense?
Yeah, a little better.
Okay. Okay, so we choose lactic acid, which has a pKa of 3.85. So now we need to determine the correct ratio of conjugate base to acid that we're going to need. Okay, so we have the equation pH is equal to the pKa plus the log. Well, there it is, right? There's that ratio of base to acid. So I know the pH is going to be 4.0. The pKa is going to be 3.85. I'm trying to solve for this ratio, so I just rearranged the equation, right? Now we're going to take the anti-log. So that ratio then is going to be equal to 10 to the pH minus the pKa, or 10 to 4 minus 3.85. Okay. Okay, so that gives us a value of 1.41. Okay, but the problem is that I have two unknowns, right? I'm trying to solve for both I am trying to solve for both the lactate ion and lactic acid. So if I have two unknowns, what do I need? If I have two unknowns, what am I going to need to solve this?
It'd be a system of equations.
Yeah, right. I need an equation for each unknown. Well, there was my first equation. Katrin, could you tell me a second equation that we could use?
The buffer capacity.
Yeah, right. So beta equals the concentration of the acid plus the conjugate base. So that's our second equation that we can use. Okay. So there it is. There's our buffer capacity. We said the concentration of the base plus the concentration of the acid is equal to 0.01. So there's our buffer capacity, total concentration. So now I have two equations. Now you could rearrange either one of these equations for one of the variables and plug it into the other equation. Doesn't matter which one you use. In this case, what I'm going to do is I'm going to take equation number one, I'm going to solve it for A minus. So that means that A minus is going to be 1.41, and I'm going to multiply it by HA. Now, in this equation, I'm going to replace A minus with 1.41 times HA. That's what you see here. Okay. Now, can you tell me what 1.41 HA plus HA is equal to? Let me rephrase it. What is 1.41x plus x equal to? What is 1.41x plus x equal to?
It's supposed to equal 0.01.
No. I literally want to know what 1.41x plus x is equal to. This is extremely simple algebra.
2.14x.
Yes. Okay. This is extremely simple. I don't even think it's algebra. It's just math. Well, no, I guess it's algebra. It involves variables. But again, it's 1.41x plus x. So it's just 2.41x. Okay. So When we do that and we solve it, we're then going to get the HA plus concentration then. So we're going to take 2.41. We're going to take 0.01 divided by 2.41, and that's where this number comes from here, 0.004 molar for the acid. Okay? So now we're going to take this and plug it into, again, either one of these equations. It doesn't matter. Plug it into either one equation and solve then for your, so I'm plugging it into this. No, I'm sorry, I'm plugging it into this. Or actually, I'm plugging it into this equation here. So I'm going to plug in the HA of 0.014, and that's going to allow us to determine that the A minus concentration is 0.006 molar. Okay, so now we have the concentrations of the acid and its conjugate base. Okay. Okay, so now we have them, those the molarities, but again, these things come in solids. We don't buy solutions of them. We're going to buy a jar full of them, which is a solid. So we'll buy, again, we're going to buy the lactic acid. And again, we can't buy a jar of formate ions because you can't buy ions. So we need to buy it as a neutral salt. So as we discussed earlier, we're going to use either a lithium, a sodium, or a potassium salt. And that's because the lithium, sodium, and potassium first are strong electrolytes, so this will fully dissociate. It's not going to mess with our equilibrium between our weak acid and weak conjugate base. And secondly, the sodium ion, lithium ion, potassium ion are the conjugate acids of strong bases. Again, therefore, they will not affect the pH. The formate ion, I'm sorry, the lactate ion will, but not the sodium ion. Okay, so we now have the number of moles, or the molarity. We're making 1 liter of solution, right? So the molarity is the same as the number of moles. So we know how many moles of each. We need 0.004 moles of the lactic acid and 0.006 moles of the sodium formate. So the mass then, we're just going to take the moles of the acid times the molar mass of the acid, and that's going to tell us the mass of the acid that we need. We'll do the same thing with the base. We'll take the sodium lactate. We need 0.006 moles, multiply it by the molar mass of the sodium lactate, and that tells us we need 0.67 grams of the sodium lactate. So what we're going to do is we're going to take a 1 liter volumetric flask. We're going to fill it up about halfway. We're going to add 0.36 moles of our lactic acid and 0.673 grams, I'm sorry, 0.36 grams of our lactic acid, and add 0.673 grams of our sodium lactate to our 1 liter volumetric flask. We're going to mix it up. Now the reaction flask is likely going to become warm. We'll let it cool down, and then we'll fill it up to the 1 liter mark and then finish mixing it off. And now we have 1 liter of a buffer solution that is has a pH of 4.0. Okay. So again, we dissolved it all in 1 liter. Okay, any questions about that? How would the pH change if I added another liter of water to the buffer? What would happen to the pH? If I added 1 liter of water to my buffer to give me, now I have 2 liters, what would happen to the pH of the buffer?
Would it become more basic?
It actually wouldn't change at all. Let me go way back here. I want to go back to the Henderson-Hasselbalch equation. See, this is the concentration, and this is the concentration. If I double the volume, well, I'm doubling the volume of this, and I'm doubling the volume of this. So they cancel each other out. So by doubling the volume of my buffer, by simply adding 1 liter of water, the pH wouldn't change at all. What would change? Would anything change?
The concentration.
Okay, I agree with you.
It would dilute. Right?
And how would that affect my buffer though? You're right. I would have a much more dilute conjugate base and a much more dilute acid. So how's that going to affect my buffer? In what way?
Well, wouldn't it dictate whether you needed more or less of something?
What do you mean by that?
Like, okay, for like in this, you wanted a pH of 4,
Yep.
and everything was according to this equation. If you change the concentrations, like if you were to, the concentration in this, it says it has like the buffer capacity is 0.01.
Okay.
That would change, right?
That would change, right?
Yeah.
That would become much less. So how would it affect my buffer? Well, my buffer would become less effective. I could add less acid or base to have a similar pH change as my original buffer. So by diluting the buffer, the pH doesn't change, but the buffer capacity is greatly reduced. So does everybody get that idea? Okay, so now the reality is you wouldn't do it this way. The easier way would be to figure out what your buffer capacity is, which is 0.01. Since we want 1 liter, that would be 0.01 moles. Well, I'm going to take the molar mass, and I'm going to figure out the mass for 0.01 moles of my acid. Then I'm going to take that mass, I am going to dissolve it in about 3/4 of that 1 liter of solution. Okay? And I'm going to mix it up and I'm going to let it dissolve. Then I'm going to take a pH meter and I'm going to stick it in the solution. And I'm going to start adding a very strong sodium hydroxide solution to it until I reach a pH of 4. That's actually going to give me the same pH as if I would have added the salts individually. So that would be the actual way that you would create this buffer. You could do it this way if you wanted to, and it would work perfectly fine. But this way will also give you the exact same results. Now, all of your homework problems are going to be based around understanding how this works. Because the more you can understand how to calculate these, the better you're going to understand how the buffer works. Understanding that changing the concentration won't change the pH of the buffer, but it's going to greatly affect the buffer capacity. So again, being able to understand all this helps you better understand how buffers work. So this is just number 18 from chapter 17. And we're going to do the problem that I was just doing. We're going to do it on tomorrow. Okay, before we do any, get back into the lecture slides, we're going to do that problem. But that takes quite some time. It'll take at least probably 20 minutes to a half an hour to go through and explain. Okay. Okay, so this is number 17, and it says how many grams, so it wants a mass, how many grams of benzoic acid. Now, benzoic acid looks like this. It is C6H5CO2H. It is a carboxylic acid on a benzene ring. So this is benzoic acid, and I'm going to call it H-ben, so I don't have to write all of that anymore. Okay, so the mass of H-ben is what we're looking for. So how many grams of benzoic acid must be added to 500 milliliters of 0.2 molar sodium benzoate? So sodium benzoate would have this formula, NaC6H5CO2. Right? So this is the plus part of it here. This is the minus part here. This is the benzoate ion. So the neutral salt then is just the sodium benzoate. I'm going to call it Na-ben. Okay. So this is 0.2 molar of sodium benzoate. And to give us a buffer, so the pH of our buffer would be 4.25. And it says ignore the volume change due to the addition of benzoic acid. So when we add the benzoic acid to it, it's going to change this volume by a small amount, right? Because the solid actually does have a volume, but it's actually a very small volume compared to the 500 milliliters of water that's there. Okay. So we're going to ignore the volume change. So basically what I'm doing is I am looking for how am I going to go about solving this problem? What equation, concept, idea, what am I going to need to solve this?
Do you want to find like an acid and a conjugate base that the pKb value falls in between where your pH wants to be?
Okay, but that's true, but it's already telling me what my acid and conjugate base are going to be. The acid being benzoic acid and the conjugate base being the benzoate, but again, in the form of sodium benzoate, as we explained before, the sodium isn't going to hydrolyze, so it's not going to affect the pH, and the sodium salt is going to completely dissociate. So this is our acid and our conjugate base in this case. So again, what equation, concept, idea, how am I going to go about solving this? I want the mass of benzoic acid to create 500 milliliters of buffer that's 4.25, knowing that the 500 milliliters is already 0.2 molar sodium benzoate.
Find the concentration of the buffer.
I did not hear any of that.
Would we find the concentration of the buffer, like using the 125?
Okay, so, okay, I kind of agree. So again, I ask, is there an equation that we're going to need to use?
I was thinking.
I'm sorry?
I was thinking if from what we did before about like finding excess.
No, not going to be necessary here.
Okay.
What equation are we going to need to use?
Would it be the equation where we use the pH buffer and reverse it to get
Okay, so the Henderson-Hasselbalch equation, right? Is that what we're talking about here?
Yeah.
So pH equals pKa plus the log of the concentration of the base over the concentration of the acid. The base and the acid. Okay. What am I solving for? I want the mass of benzoic acid. What am I solving for?
The concentration of the acid.
Yeah, right. So how's that going to help me get to the mass?
You just have to convert it with the volume.
The volume is going to give me the moles, and then how do I get from moles to mass?
The total volume.
Well, the molar mass of benzoic acid, right? Okay, so yeah, we're going to solve for the acid. So let's do that first. I'm going to rearrange this equation. So it's going to be the pH, and I'm going to subtract the pKa. So it's going to be pH minus the pKa. That's going to give me the log of the base over the acid. Then I'm going to take the anti-log. So that means then that the base over the acid is going to be equal to 10 to the pH minus the pKa. Okay, so again, I subtracted the pKa, and then I took the anti-log, which made it 10 to whatever was on that other side, right? We'll put this in parentheses. And so then I want the concentration of the acid, so I'm going to multiply both sides by the acid, and then I'm going to divide both sides by 10 to the pH minus the pKa. Again, you don't have to rearrange the equation if you don't want. I just like to because I could throw everything in the calculator all at once. Okay, so the concentration of the base was already given to us, so this is 0.20 molar. Then we have 10 to the pH. The pH was given to us of the buffer, right? So 4.25. What about the pKa? Where am I going to get that? Where am I going to get the pKa?
Your table.
I'm going to get it from the table. Now, I want to tell you this, that the pKa's aren't as accurate as the Ka's. So what I'm going to do is I'm going to look up the Ka. I'm going to look up the Ka for benzoic acid, and that is 6.5 times 10 to the negative 5. And then I'm going to actually take the negative log of that. And so the pKa then is going to be equal to something. 4.187. So again, this is more accurate than than is listed in the tables. That's why I didn't want to list the pKa's, because I don't want you using the pKa's in the actual calculations. I want you to use the Ka's that were actually determined. Okay. Okay, so now I have minus then 4.187. I'm not going to go through for the sig figs. You can look at the solutions manual, actually goes through that for you. But you got to have mixed operations, then you have anti-logs. So you got to follow all of those things. And we can see our units are going to be molar, right? So then this is going to come out to be 0.17302 molar. And this again is going to be for our benzoic acid.
When you're plugging it into the equation, is the concentration of the base actually 0.20, or would you have to consider that?
Yes. In this case, because of what the question said, okay, so the question actually gave it as a point, so it was 500 milliliters of 0.2 molar benzoic acid in this problem. The problem, the example that I showed you in the slides was different. So again, you got to read the question and figure out which method, which route you have to take to solve it. Again, this is why you got to do the homework. There's so many ways that these problems can be expressed in real life that you got to understand how to solve them in different ways. Okay, so yes, the way we solved it before in the slides was slightly different than what we did here. In here, we actually started with a solution that was already 0.2 molar. Okay, but that's a good question. So in this case, it was already 0.2 molar, so we didn't need to address it. Okay, now that we have the molarity, so again, this is 0.17302 moles of benzoic acid per liter of solution. Well, we're going to multiply that by the volume, 500 milliliters. Now, we got to do a little conversion here because they are not being consistent. So now my milliliters cancel, my liters cancel, and now I have moles. But I want the mass, right? I want the mass of benzoic acid. So now I just got to calculate the mass from the actual formula. You'll see that there's 122.12 grams of our benzoic acid per mole of benzoic acid. And again, remember that H-ben represents that entire chemical formula there, right? So that's where I got that molar mass, was from that formula. But we're just calling it H-ben. So then the moles cancel, plug it into your calculator, and you're going to get a value of 10.56 grams. This was 2 sig figs. This is 4. That's exact. This is 5. So this is 2. So this is going to be 11. Just 11. You don't even need the point. So it's going to be 11 grams of benzoic acid added to the 500 milliliters of already existing 0.2 molar sodium benzoate, is going to give us 500 milliliters of a buffer with a buffer capacity of 4.25. Now, part of this question that I would add to this, well, first off, before I say that, does anybody have any questions about this? Now, another question I could have asked you on the exam after I asked you to calculate this was, okay, what is the buffer capacity of this solution? Can anybody tell me? The exact value of the buffer capacity to 2 sig figs. Could anybody tell me the buffer capacity?
Is it 0.37?
It absolutely is, right? The buffer capacity is nothing more then the sum of the concentration of the base, in this case, the sodium benzoate, right? This is our base, plus the concentration of our acid, which in this case is the benzoic acid. This is our acid. And so the base was given to us as 0.2 molar. And the acid concentration we determined is 0.17 molar. That would have given us 0.37 molar. So our buffer capacity was 0.37 molar. So that would have been the buffer capacity. Any questions? So for example, let's say you want a buffer that is, I don't know, a pH of 6. What you're going to do is you're going to come down here and you're going to look which one is closest to 6. So here's a 6.37, right? And we want to be within plus or minus 1. So we would choose an acid that had a pH. If we're looking for a buffer of 6, we're going to choose an acid between 5 and 7. And closest six that we could possibly get with whatever choices you have, right? So here's a 6.37, so that would work. That is our carbonic acid. Would you use carbonic acid as your buffer?
No, because it would neutralize and form a gas.
Right, it would decompose into carbon dioxide and water. So that would be a bad buffer to use. Now our body can do that because of the way it works, right? But we would never use that buffer in the lab. But then we can come down here and we see we have a buffer of 6.52. So where the heck did I just see that? There we go. So there's the buffer 6.52. So that would be the hydrogen chromate ion. That again would actually be a bad buffer because this is actually not the full acid. Okay, so we might not want to choose that buffer. So keep them coming down then. Go on to the next page. Those are what we want. So we're not going to be able to choose that. So instead of being above, let's go with something in the high 5s. Okay. So to make a buffer of a pH 6 is going to be pretty difficult with the acids that we have here to choose. We might actually end up outside that plus or minus 1. I guarantee on your quizzes and your exams, that won't be the case, okay? Let's go to a buffer, let's say, of 2. So if we wanted a buffer that had a pH of 2, a good choice there then is going to be the chlorous acid, okay? Because that's real close to 2. And what that means is that our concentration of acid and conjugate base is going to be almost equal to one another, which is great for buffer capacity. What would be, so if this is the acid, what would be the conjugate base that you would choose? So if HClO2 is our acid, what base would you choose?
Chlorite.
Say again?
The ClO2, so solely.
But ClO2 is an ion, and you can't have a jar of it.
So like sodium chloride or something.
Exactly, right? Sodium chloride or lithium chloride or potassium chloride. Generally, that's all we're ever going to use, or sodium, lithium, and potassium salts. I mean, unless there's some other reason you have to use something else, you want to use those ions, again, because they don't hydrolyze, and they're always strong electrolytes. So whatever your conjugate base is, you're going to use a sodium, lithium, or potassium salt of it. Does that make sense? Okay, now let's say it's a basic buffer. Let's say you want, and again, I haven't prepared this ahead of time. So we're just going to say, let's say it's a pH of 10. Well, now you got to go to your you got to go to your bases, right? Because you know if you have a pH of 10, you're going to need a base rather than an acid. So now what you're going to have to do is you're going to have to go, if we want a pH of 10, well, we're going to have to take, this is the PKB. So if that's the PKB, what we didn't talk about is that if you have a PKB, the pKa plus the pKb are related to one another. So for example, let me just show you real quick. So if the Kb is going to be equal to the Kw over the Ka, that's going to be 1.0 times 10 to the negative 14 divided by, and we're just going to choose this guy right here, ammonia, okay? That's going to be over 1.76 times 10 to the negative 5. And so when you plug that into your calculator, you're going to get 10 to the negative 14 divided by the quantity of 1.76 times 10 to the negative 5. That's going to give you a PB of 5.68 times 10. This is a K. This is a Ka because we're actually looking at the Kb, right? So this is a Ka and the Kb. So that's going to be equal to 5.68 times 10 to the negative 10. And if we take the negative log of that, okay, so if we take the negative log of that answer, that's going to give me 9 point, so this is then the pKa, which would be 9.2, and that's 5, so that's going to be 2.5, okay? So an easier way of doing this would have been if I simply take 14 minus 4.75, look, I get the exact same number. So pKa plus pKb is actually equal to 14. I should add this to your notes. Okay. So I didn't used to have this in my tables, and so you always had to do it this way. But then I realized for exams, you just don't have enough time to put the values in. Okay. Does that answer your question?
Yeah, that makes sense. Thank you.
Any other questions before we get started? Okay, let's pick up then where we left off. Yesterday we actually started doing this problem and we just quit because I realized it was going to take too long. So number 21 says calculate the pH of a buffer that is prepared by dissolving 2.28 grams. So we have 2.28 grams of hydrazine, which is again, you all should recognize that as what? An acid or a base? What do you think hydrazine is, an acid or a base?
A base.
Yeah, right. Again, we have these neutral nitrogen-containing molecules, and they have lone pairs on these nitrogens, which can be a proton acceptor. And so again, we know that our neutral nitrogen-containing molecules are bases. They're soluble because they have identical intermolecular forces that water does. So like dissolves like. So this is going to act as a weak base. Okay, so calculate the pH of a buffer prepared by dissolving 2.28 grams of hydrazine and 1.98 grams of hydrazinium chloride. This, of course, would be our conjugate acid. Okay, so this is our base, and this is our acid. In 100 milliliters of water, so that's going to be important. We'll answer the second part of this next, but let's just first calculate the pH of this buffer. So, of course, if it's a buffer, the first thing that should come to your mind is what? And again, I'm trying to develop your thought process when you're solving these types of problems. So as soon as you hear buffer, what do you think of? When we're trying to quantify a buffer, what do you think of? Well, you should think of the Henderson-Hasselbalch equation, which says the pH is equal to the pKa plus the log of the concentration of the base over the concentration of the acid. So we're going to have to determine the concentration of our base and the concentration of our acid. Concentration, of course, is going to be moles over liters. So this 100 liters, right, if we divide that by 1,000, since there's 1,000 milliliters in a liter, that is going to give us 0.10000 liters. So there's our volume, 0.10000 liters. And now, of course, to get this to moles, all we got to do is divide that by the molar mass. So there are in hydrazine, there is 32.045 grams of hydrazine per mole of hydrazine. So the grams cancel, and that's going to give us our units of moles per liter, exactly what we would expect. And so this is going to give us a value then of 0.71149 molar. And we got 3 sig figs, we got 5, so this will be 3 sig figs. Okay, now we're going to do the same thing for our acid. So again, it's in that 100 milliliters. And we're going to divide this by its molar mass. So in 1 mole of hydrazinium chloride, there is 68.506 grams. The grams of hydrazinium chloride cancel, and then plug that into your calculator, and you're going to get a concentration of 0.28902 molar. And again, 3 sig figs, 5, 5, so this will be 3. Okay, so now we got the molarities, but we need the pKa. So I'm not going to find a pKa for our acid because that's actually a conjugate acid of our base. So I need to look up, of course, the Kb. Okay, so I'm going to look up the Kb of hydrazine, and that's going to have a value of 1.3 times 10 to the negative 6th. But I need the Ka, and again, we know that Ka times Kb is equal to Kw. So the Ka is just going to be the Kw over Kb. So that's going to be 1.0 times 10 to the negative 14 divided by our 1.3 times 10 to the negative 6th. And that is going to give me a value of 7.692 times 10 to the negative 9. Okay, now we're going to plug that in because all we want is the pH. So the pH then is going to be equal to the pKa, which is just the negative log of the Ka that we just determined. Again, I would not encourage you to use the pKa values. On an exam, I wouldn't care. But on Canvas, Canvas is really, really picky. Okay, and this is more accurate than the pKa value that's given in the tables. So, so on the quizzes, make sure you take the negative log of the Ka or the negative log of the Kb to get the value that you need. Don't just use the values listed in the book, okay, or in the tables of chemical data. Okay, so then it's going to be plus the log of the base. Well, the bases are 0.7114 molar, and our acid is 0.28902 molar. And so, of course, the molars cancel. Now, you could have solved this in a different way, right? You could have just used moles. We could have just used moles of the two. Because again, this is going to cancel this in this ratio. But that's fully up to you. That usually works. There are situations where that doesn't, and you'll have to look at that. But that usually works where you could ignore the volumes and just put moles in here. Because again, it's all in the same container. So your volumes are going to almost always be the same. Okay. So then plug all that into your calculator, and you're going to get a value of 8.5051. Now here we took the log of this value. This ended up being 8.1139. Since that's 2 sig figs, this would be 2 significant decimal places. And then here we actually have mixed operations. But whatever this is, it's going to have the 2 sig figs. And so it's going to come out to be 0.39121. Oh, I screwed up. These each have 3 sig figs. 3 sig figs. Okay, since they have 3 sig figs, we'll have 3 significant decimal places. Now we're adding, right? So we're adding these 2 values. So we're 2 past, 3 past the decimal place. So this can only be the least precise, which is 2 past. So that'll be there. So basically, this buffer started out with having a pH of 8.51, which is, of course, greater than 7. And so it's a basic buffer. Okay. Any questions about this part of the problem? Okay. Then, so again, we'll come back to this. We'll come back to this original buffer, but the second part says, how would the pH change when 10 milliliters of 0.2 molar HCl is added to our buffer solution? So basically, we have the buffer, which is just hydrazine and our acid, which is the hydrazinium chloride. Now, the hydrazinium chloride, of course, is a strong electrolyte because most salts that contain the chloride ion are soluble with the exception of silver, mercury, and lead, and that's not silver, mercury, or lead. The chloride ion is the conjugate base of a strong acid, so it's not going to hydrolyze. In other words, it's not going to affect the pH. So the only thing we're really worried about is the ion, the conjugate acid itself. And of course, in a buffer system, it looks like this, right? We would actually have this dissociating, the acid dissociating into the base and the H+. So if we're going to add acid to it, right? We're going to add acid. So we're going to add acid. We're going to assume that all the acid we add is going to react with the base. So that means we're going to lose the same number of moles of base as we added acid. But what else happens when we do that? We can't create nor destroy matter, right? Law of conservation of matter. So what happens to this base? So if I lose as many moles of base as I added H+, what happened to the base? It becomes the acid. So as many moles of H+ that I add, I'm going to lose that many moles of base, and I'm going to gain that many moles of our conjugate acid. So I now need to calculate the new concentrations, right? So I now need to know the moles, or again, this time I'm just going to use the moles. Since we know that the total volume is going to be the same, let's just use the Henderson-Hasselbalch equation, but this time we're just going to use the number of moles. So again, we're looking for the pH of this solution afterwards. So again, we're simply going to use, since it's a buffer, we're going to use the Henderson-Hasselbalch equation. So the log of the concentration of the base over the acid. But now that we're adding this strong acid, right? This is a strong acid. And so it's just going to dissociate into H plus and Cl minus. And again, the Cl minus is the conjugate base of a strong acid, so it's not going to hydrolyze. And the H plus coming from this strong acid is what we're adding, what is going to react with the base to form more of the conjugate acid of the buffer. Does everybody follow what's going on here? Does anybody not understand? Okay, so let's calculate then. So we're going to now need the number of moles, and let's start with the base first. So this is going to be the number of moles of base, and this again is after the acid is added, right? So after acid is added, that's what we're looking at here, okay? So the number of the moles is going to be the original number of moles, okay? So again, you could have just calculated the number of moles from the first part, okay? And there's a bunch of ways you could do it. You could just calculate the number of moles themselves, or we could take the concentrations that we started with. Okay, so I could have just calculated this and used that. That would have probably been the easiest way, and not have actually used liters at all, right? Then I would have calculated the number of moles. But let's just use the molarities, right? So since this is 0.71149 moles, and again, like I said, there's many ways to do this. I don't care how you do it as long as it's correct. I just don't want to confuse you with too many different ways. Okay, so I could just multiply this by the volume of the buffer. Okay, so remember, that's the volume of the buffer. So that is the 0.10000 liters. So that's going to cancel, and that gives me moles of the base, right? So this is the original moles of base. Now remember, we're going to lose a mole for every mole of H plus. So we're going to say subtract. Okay. And now we're going to calculate the moles of the acid. Well, again, since it is going to be, since it's 0.2 molar HCl, and it's a strong electrolyte and completely dissociates, that means this is going to be 0.2 molar, and this is going to be 0.2 molar, since it's a 1-to-1 ratio with HCl. We don't care about the chloride. Again, that's the conjugate base of a strong acid. It's not going to hydrolyze. But the H plus is going to react with our base. Okay, so we're going to lose that many. So then we have, so again, we have the 10 milliliters, which is going to be 0.0100 liters, right? So this is just 0.01100 liters. That's what this is here. Okay. Then we have 0.2 moles of H plus or HCl per liter. Our liters cancel. And again, I can see that from this equation, it's a 1-to-1 ratio. So for every mole of H plus, it's going to react with 1 mole of our base to form that many moles of acid, right? So what's left then is this difference, and this then is just going to equal, so it's going to be what, 0.028902 moles minus 0.0020 moles. This is sig figs there. This here was 3 sig figs, so this will be 3 sig figs. So this is going to give us then 0.030902 moles of our base. And that'll be what, 1, 2, 3, 4, 1, 2, 3, 4, so 1, 2, 3, 4. Okay, so any questions about that? Okay, now we got to do the same thing with the acid of the buffer, right? Well, we lost this many of the base, but we gained that many of the acid. So the moles of acid then, again, is going to be the original moles of acid that we calculated in the first place. So again, we're going to get that from the molarity. So the molarity of that original solution, again, was 0.28902 moles of our acid per liter solution. We had the 100 milliliters of the original buffer solution that we added the acid to. So that cancels. So this is the original moles of acid. But now we're going to gain, right? We're going to gain acid because every one of these that reacted with this formed an acid molecule. So again, that's going to be the 0.0100 liters of our 0.2 moles of H plus per liter. And again, we can see it's a 1-to-1 ratio. So for every 1 mole of H plus, we formed 1 mole of our conjugate acid. So the moles, liters cancel, and we have moles of acid plus moles of our acid. Plug that in, and you're going to get 0.71149 moles minus 0.0020 moles. This again was 2 sig figs. This was 3 sig figs. Put that into your calculator. You're going to get 0.069149 moles of our acid. So this is 1, 2, 3 passed. This is 1, 2, 3, 4 passed. So this can only be 1, 2, 3 passed. So that'll be put at. Now I forgot a 0.
The moles of base and moles of acid, I think the intermediate step is switched because the original moles of base wouldn't be 0.0289, it would be the 0.071149. Does that make sense?
Yeah, I'm sorry, you are correct. I did flip them. So this is really, this whole calculation is for that. This whole calculation is for that. Sorry about that. There we go. Why would I flip that like that? Okay, so sorry about that. So we've flipped the two, except this is plus then, plus. Does that make sense? Yeah, and this is minus. And I have the minus there already. Okay, so we're good now. So again, we lost our base when we added DH plus because it reacted with the base to form new acid. So we gained that same number of moles of acid. Now we could convert these to concentrations, right? Like it shows here. But the new volume is 10 milliliters plus 100 milliliters. So don't forget that. If you're asked to calculate molarities, or what we're going to see here shortly when we're calculating the pH at the equivalence point of titrations, we're going to have an original volume of a solution, and then we're going to add another solution, a given volume of another solution. So at the equivalence point, that would be the total volume. So in this case, the total volume would be the 100 plus the 10 milliliters, which would give us a total then of 110 milliliters. Okay. But like I said, since they're going to be in the same, and we know the volumes of both of these are the same, we could just use the moles. Now we've already established again from the first part of this problem that the Ka was this value here. So, and then actually we calculated it. So it ended up being this, right? 8.1139. And then we now have the new base and acid concentration. So the base was our 0.069149 moles. And our new acid is 0.030902 moles. Okay, so now you plug that into your calculator. So that is going to be equal to our 8.1139. And then this will be plus the log of this is going to be 0.34979. And that's going to be the 3 sig figs. And so this is 2 past, this is 3 past. So our answer can only be 2 past. And so that'd be 8.47. I'm sorry, 8.46. Okay. So what would we expect to happen to the pH if we added an acid to a basic buffer? What would you expect? What would happen to the pH of a basic buffer if we added an acid to it? Would it increase or decrease? If it became more basic, this number is going to become bigger, right? Because the base is greater than a pH of 7. If it becomes more acidic, we're going to expect it to decrease. So to check your work, the pH of the buffer before we added the acid was 8.51. The pH of the buffer after we added the strong acid, okay, a 0.2 molar solution of strong acid, it only changed by 0.05. But it did decrease. It became more acidic. It's still basic, right? But it became less basic at 8.46. Any questions about that good stuff? So again, when you're doing these problems, you got to make sure that you have a game plan before you start. That game plan involves understanding the chemistry that occurred. So again, when you're adding a strong acid or a strong base to a buffer, if you're adding a strong acid, the acid's going to react with the base. You're going to lose that amount of base, but gain that same amount of acid. Vice versa, if we added a strong base, let's say we added sodium hydroxide to this buffer, the hydroxide would react with the acid and would lose that amount of acid, the same amount of hydroxide that we added, but we would gain that much base. Okay, so just make sure that you're going into these problems with a game plan and not just willy-nilly solving them, because that's going to take forever, number one, and number two, you're probably never going to get to the correct answer. So any questions about this?